Hi guys, in the last class I have given one homework question. How many of you got the answer? If you got the answer, kindly drop it in the comment section. Let us see the answer for this question. So before entering into the lecture, if you are really understanding whatever the content that I am delivering here, don't forget to share it with all your friends and also don't forget to click that like button. Okay, let us start the lecture. See, this is the given. The question is mu and Cx is given for both transistor and also threshold voltage is given for both the transistor. We have to identify the value of Vx. Rest of all data is given. Now let us start involving into the question and try to bring the answer. First, let me take the current entering into the first transistor is ID1 and the current entering into the second transistor is ID2. Yes or no? Yes sir. And what is the expression for current? Can you write the answer directly? No sir. In order to know the expression for the current, we have to identify the region of operation. Because we have two different formula for drain to source current, it depends on the region of operation. It may be linear region or it may be saturation region. Now, if you keep your attention with the second transistor, see, let me call this one is second transistor and this one is first transistor. Second transistor, if you observe the second transistor, the gate terminal and the drain terminal are shorted together. It means what? I have already given the note. What is the note? Whenever in any Mosfet, if you are observing that gate and drain terminal are shorted, then directly you can make the conclusion that that Mosfet is being operated in saturation region. So we found that one transistor is being operated in the saturation region. But what we have to do is we have to do the similar thing for the second transistor first transistor also, because in first transistor we don't know in which region transistor 1 is being operated. For that, what we have to do, take the first transistor outside, collect all the data for the transistor 1. If you observe, for the transistor 1 the value of drain voltage is given as 6 voltage and the value of gate voltage Vg1 is given as 5 voltage, and whereas the value of source voltage Vs, it is for the first transistor it will be equal to Vx. Yes sir, of course that is correct, that is equal to Vx, and Vx also equal to drain voltage of the second transistor and that is also equal to gate voltage of the second transistor. If you observe, Vx is fixed at the common terminal of the second transistor gate and the second transistor drain, first transistor source, all are connected together at the junction. That junction point only we are measuring now. At the junction only we are going to calculate the voltage now. Okay sir. Now let us proceed further. From this, if you take the first transistor, we have to identify the value of VDS1. This can be further written as VD1 minus VS1. Do you have any idea about VD1? Yes sir. VD1 is 6 voltage minus VS1. Of course that is simply called Vx. Okay sir. As of now I am fixing it. Similarly, if we keep our attention with the gate to source voltage VGS1, this can be further written as VG1 minus VS1 equal to the value of Vg also given, that is 5 minus VS1. Now the next step is we have to calculate the value of VGS1 minus Vt in order to know the region of operation. So this can be further written as VGS1, just now I have written 5 minus VS1 minus Vt equal to 1. So this can be further written as 4 minus VS1. Now if you observe the relations, VDS1 can be written as 6 minus VS1, whereas VGS1 minus Vt can be written as 4 minus VS1. It clearly indicates that, see, whatever the value for VS1, forget about it. It is, see, observe, it's clearly, here we are having 6, here we are having 4. What is this? In both cases we are having Vs only. Suppose if the value of Vs is 5 voltage, then what will happen? VDS1 equal to 6 minus 5, we are getting 1. Similarly, sorry, I can't take 5, it will be wrong relation. 1 minute. Suppose if it is 2 voltage, then VDS1 will be 6 minus 2 will become 4. VGS1 minus Vt, 4 minus 2, this will give you 2. What is the conclusion? This relation clearly indicates that the value of drain to source voltage is greater than the value of gate to source voltage minus threshold voltage. Okay sir. Once this condition is satisfied, then you can clearly say that the resultant answer. Sir, whenever VDS is greater than VGS minus VT, then the region of operation for the transistor is saturation. So always remember one thing. It is not required to know the all data. In this case, source voltage is not known, but we can easily identify the region of operation. So just to try to derive with the given data. See there, I have derived only given data. I haven't brought anything and I did not kept any assumptions here. So I just went up with the given data and I found the relation. So finally the conclusion is, already we found that MOSFET 2 is in saturation region. Now we found that MOSFET 1 also in saturation region only. Since both MOSFETs are in saturation region, how can you write the expression for current flow through the drain to source? Let us write the expression. For the first MOSFET, let me write the drain to source current for the first MOSFET. Since it is in saturation region, so I can write constant K by 2 or mu ox is given, right? So let me write everything. Mu n C ox omega by L. Let us consider the 2 here. In bracket, it is going to be VGS minus VT whole square. So I am calling it as VGS 1 because I am writing the expression for the first current. Similarly, ID2 equal to mu n C ox by 2. Here it is going to be omega by L, and here this one also is differ in our case. They have given two different value. So I am writing it as VGS2 minus VT whole power 2. See, internally these parameters may have different values, like omega by L is different from first transistor, and they told VGS1, VGS2, they are differ. But if you keep your attention with the circuit, since through the gate terminal there will be no current, and MOSFET 1 and MOSFET 2 both are connected in series directly. See there, it is in cascaded connection. So whatever the current that is entering coming from drain to source, same current will be entering into second transistor or not. So let me tell you how that configuration is connected. Drain current will be coming from the first MOSFET. It is crossing drain to source terminal. So same current will be entering here. From drain to source, same current will come from the first MOSFET. Now whereas source terminal of the first transistor directly connected with the drain terminal of the second transistor. So I can say, whereas the second MOSFET will going to carry the current is called I2. That current is simply coming from here only, because you don't need to be bothered about the shorted gate terminal. Gate will not consume any current. If you observe, the second transistor is connected in the second transistor, gate terminal is connected with the drain terminal, but it will not consume any current. We know gate current is always 0, since MOSFET is acting as a voltage controlled device. So what is the conclusion here? Whatever the current that is entering into the second transistor, same current is coming from the first transistor. So I can write ID1 is always equal to the value of ID2. From this, we can equate these two equations. If you will equate, then what you will be getting? Let me write mu n C ox by 2. It is given as omega by L 1 into, in bracket, it can be further written as Vg1 minus Vs1 minus Vt whole square equal to, on the right hand side, mu n C ox, I can write C ox by 2 omega by L 2. Again this can be further written as Vg2 minus Vs2 minus Vt whole power 2. Now you know mu n C ox is 100. See, it is clearly given in the question. It is 100 microampere per whole square. Observe here, it is common for both. And Vt is 1 voltage. Similarly, for the first transistor, W by L is 4, second transistor W by L is 1. So let us substitute all the values. First transistor W by L is 4, second transistor W by L is 1, and this mu and Cx is common for both, so it will be cancelled out. I can directly cancel it, and this threshold voltage is given as 1 volt, so you can replace it by 1. So this is also going to be 1 volt. Now what is the value of Vg1? Vg1 is given in the question. The value of Vg1, this is the gate voltage, Vg1 equal to 5 voltage. Okay sir. So Vg1 is 5, whereas Vg2 equal to Vx. Yes or no? Gate terminal is connected with the Vx terminal only, so I can replace. See, Vg2 is considered as Vx, whereas Vg1 is going to be 5 voltage. We know Vs Vg to Vs1, that is source terminal of the first transistor, drain terminal of the second transistor, gate terminal of the second transistor, all are connected with the Vx only. So the conclusion is Vs also going to be replaced by Vx. Vs1 will be replaced by Vx. What is the value of Vs2? Source voltage, it is connected with the ground. So Vs2 equal to 0 voltage. So you can replace it by 0 now. Sir, I am going to replace it by 0. Finally, if you reduce the expression, what you will be getting? This is going to be 4 into Vg1 replaced by 5 minus Vx minus 1 whole power 2 equal to, this will be 1. W by L is 1 only, right? So for the second one, and this is going to be Vx minus 0 minus 1 whole power 2. Again, I am going to take square root on both sides in order to cancel these squares. So what will happen? This square will get cancelled and the square root of 4 will become 2. So 2 times of 5 minus 1 will become 4. So directly we can write this one is 4. This is going to be 4 minus Vx equal to Vx minus 1. Further, if I will multiply it, this inner product will become 8 minus 2 times of Vx equal to Vx minus 1. So if I will pass this minus 2Vx to the right hand side, it will become 3 times of Vx. Bring that minus 1 to the left hand side, that will become 9. So once again the value of Vx will become same 3 volt only. So that is how we are bringing the answer for the given question. I hope you all got the clear idea regarding this current at all. Now I'm at least now you might got the clear idea regarding this. Okay sir, so this is all for this lecture. Remaining things we will see in the next class. Thank you all.